Hello, everyone. This is the first lecture on quantum mechanics. Chapter 1, the wave function. So, the first thing we're talking about is about the Schrödinger equation. In classical mechanics, we solve the classical mechanical problems by this simple procedure. So, first we find the potential V, and then we compute the F by differentiate this potential by X. And then solve the Newton's second equation, F equals mx dot dot, and we find the x. When you find the position of the particle, the other mechanical quantities comes out. X dot, velocity, x dot dot, acceleration, and p, momentum, and t, kinetic energy. However, in quantum mechanics, we choose another method. First of all, we solve the Schrödinger equation, and then we get a wave function, psi xt, and then any other physical quantities comes out. Here is the Schrödinger equation, and you'd better to memorize it for further discussion. If you see the structure of this equation, it is a basically very simple second order partial differential equation, PDE. So I is, you know that, period of minus 1. Bar, you know that, h divided by Planck constant divided by 2 pi. And here's psi, the wave function, is partial differentiate by t. And then here, square over 2m, and second partial derivative by x of this psi, and plus potential v psi. We can rearrange this equation like this. I have a partial t psi equals to the minus square over 2m partial xx plus v and psi. We call this operator term as h. This is sometimes called Hamiltonian operator. So this equation has a very simple form. I have a partial t psi equals to h psi. So, what does that mean? What does it mean that we get the psi? Psi is basically a wave function, but what is wave function? Actually, wave function itself, it doesn't mean anything. But here is a statistical interpretation by Born. Born statements is here. When we take the norm of psi, what does it mean? Psi is actually a complex number, so a complex value can be normed by producting of the conjugate of psi and psi. So here, this norm square of psi means that probability density. So when we calculate the integral from a to b, norm of psi xt squared dx, we get a probability of the particle from a to b. More precisely, probability of finding the particle between a and b at time t. X is used as dummy variable for integration, so this left-hand side is a function of t. So, as you can see, even if we find out the psi, the nature of the quantum mechanics psi, all the information is encoded in that psi, there is a natural indeterminacy in quantum mechanics, since even if we know the psi, the only we can know is the probability. So it means that we cannot any clues to find out the exact position or exact velocity or exact momentum. That is called indeterminacy of quantum nature. So here is some note about measurement. Before measurement, a particle does not have a precise position. But right after the measurement, when you measure its position, psi collapses like this. Why is that? Intuitively, we measure some position of a particle, then the position is measured. That means that the probability on that site is peaked. As time goes on, the psi is spreading out. Here is a very popular experiment about electron interference. So here's an electron gun, and here's a double slit, and here is a screen. If you imagine the electron gun is shoot the electron one by one, then the electron, the respective electron will go through either this first slit or second slit. Remarkably, the outcome is like this. Here is 8 electrons is screened on it, and 270 electrons and 2000 electrons, and wow, here's a vast amount of electrons is screened, and there is some pattern. What is the pattern? This is the classical interference pattern. Even if we think electron as a particle, the pattern occurs. But pattern is the nature of wave. So we have to think of electron as a wave in this situation, even if we shoot the electron one by one. If we block one slit, there is no interference. Why is that? The boundary condition of Schrödinger equation alters. If we detect which slits allows the electron goes through, no interference. Why is that? If we put detector on it and detect whether this slit or another slit, then we measure the circumstance which of the detector allows two electrons goes through. It means that we measured it. So about measurement collapses the psi wave function. So wave function is collapses like this peak, and there is no longer wave nature of electron at that site. So psi collapses by the detection. This is the reason why. And third, about probability. So as we can see that the probability and indeterminacy is the quantum nature, we have to know about the basic theory of the probability and statistics. So here's that. Pj means that probability of state j, and this bracket j means expectation value of j computed by this simple formula summation over j pj. This bracket of fj also computed by this simple formula, and here's a variance. A sigma square is the expectation value of square of delta j, and sigma of course is square root of the bracket square of delta J, we call it as standard deviation. And here is very useful formula between the sigma square and J squared. Sigma square is equal to the expectation value of J squared minus square of expectation of J. Very simply computed. We just expand this inside, and then we give all the bracket entity by entity and get this simple formula. We've talked about the discrete variable. When it comes to continuous variable, the Pj is replaced by this rho x, probability density. So what does it mean? If we integrate the rho x from a to b, we get a probability ab. And here are very important facts. If we integrate whole space, we get a 1. Why? Because the whole space, if we integrate whole space, we get the whole probability, which is 1. And then expectation value of x is integrate whole space by x rho x. Also, expectation of fx can be computed similarly. Here is also sigma square formula hold. Next, we're gonna solve a problem for the Gaussian distribution. The Gaussian distribution is here of the form exponential of some minus x squared. This is just translation. This is just multiplicative factor. And here is the graph. So first, we have to determine a. So what we have to do is just normalize it. What does it mean by the normalization? If we integrate the rho x in a whole space, we get a 1. So here, integral r rho x dx equals to integral r a e exponential minus lambda x minus a squared dx a integration r exponential minus lambda x minus a squared dx. A is popped out. And here, the same with the translation value of integration. Since the translations doesn't change any integral value, this area doesn't change it. So we get a as square root of lambda over pi. And next, we're going to find the expectation value of x and x squared and standard deviation. So we use just definition. So bracket x equals to integral r x rho x dx. And then here we just translate it like this. And then we expand it and split into the two parts. And here, the first part is just can be dealt with very simple method, trick in integration. Just use the change of variable. Let lambda x squared to u squared. We get this, and next procedure is very simple, easy. And second part is just the Gaussian integration. So we get the expectation value of x is a, and this is very intuitive. Why? The expectation value of x is just the position which makes the maximum value. And here we get a expectation value. the method for finding the expectation value of x squared is exactly the same. But here, this, if you see this expansion part, the A part is some kind of tricky. The second part is just 0 y. This is just odd function integrated by whole space. And last part is just a Gaussian integration. So let's take the first part. The first part, A, let A be integral over whole space R x squared exponential minus lambda x squared dx. We know that this Gaussian integral formula, if we differentiate both sides by lambda, we get this formula. And as a conclusion, we get this. So just adding two terms, we get this simple conclusion and this as a expectation value of x squared. Lastly, we have to find the standard deviation, and we will use this very useful formula for finding the standard deviation square root of expectation value of x squared minus square root of expectation value of x. So square root, just plug in it. Plug this in and plug where is a. So we get the simple outcomes. So if you see this, when lambda is getting bigger, sigma is getting smaller, which means that sigma means the deviation. The deviation, when the deviation is getting smaller, the difference between the values is smaller, meaning the graph of the Gaussian narrower is getting narrower. What does it mean? The A is the multiplicative factor of the Gaussian, and we got the lambda getting bigger, which means the sigma standard deviation is getting smaller. So lambda bigger means A bigger. A bigger means the multiplicative factor is getting bigger, meaning the bell is narrowed like this. Very small standard deviation. Okay, that's it. Here was the first lecture of quantum mechanics. If you enjoyed it, please subscribe and like. And most of all, enjoy the physics. Bye bye.